Hey everyone, and welcome back to Teaching a Computer Your Conlang. So today's episode 2, we're going to be talking about n-gram models. So I have up on screen our goals for today and what we're doing next time, but most importantly, our goals for today are 0 with goal. I've already made the corpus, and so you can see, or the corpora, because they're multiple. So you can see over here, I've inputted all of the publicly available, plus some, but mostly just publicly available delineated text into marked and unmarked corpora. So the unmarked is just line by line, exactly what I have on screen for my YouTube videos. And then marked is that plus dashes inputted for morphological breaks. And I can talk a little bit about how I did the breaks later, but basically in another video, but basically I didn't try to break for derivation unless it was very obvious and a productive derivation. I usually just broke for things like tense suffixes and part of speech changing suffixes. So you can see all of those corpora here. So yeah, that's the corpora that we're working with. And the reason we need all this is because n-gram models are all about predicting the next token, and token can refer to a word, a phoneme, a syllable, a morpheme, a character. It can refer to any of those, and it's just saying what's the next item in a sequence based on the probabilistic readings of the stuff in the corpora. How often does su appear after miranno? Or how often does O appear after ANN? That's what the n-grams are trying to look at. So yeah, let's get right into it. So basically, we're just going to dive right into coding this n-gram model. So the first thing we have to do is read in our corpus. So let's create a new file in episode 2. We can call this readin.py, which means Python file. So we're going to import some useful packages. We're importing numpy. And by the way, you really, this is not a Python tutorial series, right? So you kind of can just copy what I'm doing for most of this. You can go look stuff up if you want to know what they actually are. Like NLTK is Natural Language Toolkit. I don't even know if we'll be using it, but it's just helpful to have there in case. We can always delete it later. Math, random, they're kind of what they sound like. NumPy is very similar. So yeah, so let's start with creating our corpus. So we're gonna define a function that will read in a file into a specific corpus. So this function, we're gonna use this code, which basically says we're gonna open whatever file name we put here, whatever file path, as a text file. Or, I mean, not as a text file. This is just what we're going to call it. And the contents of the file are going to be, we're just going to read the file. Like, you don't really have to know how this works. But it's basically just looking at these text files and it's going line by line and it's reading them. And why line by line is important is because we're doing lines. Here we're splitting them by this thing. What's \n? This is just the inherent character that your computer has. At the end of each of these lines, it kind of inputs \n just to tell the computer that it's a new line. So we're splitting it by this, which means lines is going to be a list of items, and each item is going to be a line of whatever file we give it. Awesome. So then we're going to say for each line, the stripped line is the line .rstrip. This just means there's no extra white space. And then we're going to have our corpus and we're going to append the stripped line to the corpus. This just means the corpus is going to be some list of lines, and we're going to add the line that we just had for each line into the corpus. All right. So then we're going to So then we're going to create our list of lines. So line list, it's just going to be our list of lines. The hashtag just means it's a comment, it doesn't affect the code. If you haven't used code before, if you haven't used Python before. So yeah, here's our line list. Now we're just going to do read in with all of the files that we have over here. So read in. So now we have to go like the file path of our thing. So first, we're in this folder episode 2. So we're gonna go ... which means go outside of this folder, up one folder kind of, into this bigger folder, Simulangers. Then we're gonna go corpora, because that's the folder. And let's do unmarked first. Unmarked, so that's the subfolder. And then avatar, that's the first one we have. And we're gonna read it into the corpus called line list. And then we're just gonna do this. Actually, let's just keep it at avatar for right now. Maybe it would be helpful to do this in one of these instead of just a basic Python file. So I'm gonna do that. I'm actually gonna transfer. This should not be called n-grams and CFGs. We're gonna be doing CFGs next time. But yeah, so I'm going to go over here. This should be code. Python, awesome. So we're gonna run this code. It's reading in this corpus or this file into this corpus. That's why it's taking a few seconds. And always just importing packages takes a little while. So yeah, we've read in our thing. So now something we can do just to check if we've read it incorrectly, we can say print line list. Let's say the first four lines. Hopefully this should work. Oh, I used something wrong. That's what I meant. So here we go. We have from avatar, it should print out the first 4 lines, each as an item in this list. And what does it do? It does exactly that. We have this line, and then one more line. Yeah, one more line. So that's doing exactly as we want. Awesome. So now what we can do is we can go back, since we know that works, and read in all of the rest of the files in our corpus. We can just probably copy and paste this many times. Boop. All right. And so now instead of avatar, we'll say dolphins. We'll say gush. And the ones that you haven't seen yet, I'll probably put on my channel at some point. Nyamarupachi. Pokemon. Rickroll. Yeah, you haven't seen that yet, but it's coming. It's coming. The Dutchka. The Last House. And Tikundo. Awesome. So now it should read in all of these files. So another thing we could do is we can print a random line from all of these. So, or we can print 2 random lines. So we can say, let's say, random integer, it's random rand int. So this is using the package random we have above. Let's say between 1 and the length of the line list. This one. 0. And then we'll do random integer. And it should print out a random line. So, so that one's from Gashi. This one's, I don't know where that one's from. Or this one. I think that one's probably from The Last House, which I haven't posted on my YouTube channel yet, but basically we're just printing out random lines from the corpus. And it's working. Awesome. So to go back to our goals, right? We're trying to make n-gram next token predictors. So how n-grams work, let me just do how n-grams work. How n-grams work. So if an n-gram has a corpus that only consists of one sentence, the dog ate the cat, that's its whole corpus. How the n-gram model is going to work, or how we want it to work. It could work for characters, phonemes, words, morphemes, whatever. But let's just do it for words because I think that'll be easiest to see. So for the dog ate the cat, it's trying to predict to the next word. And this is how like all of our, common AI models work nowadays, but they are more complex than n-grams. But we're starting simple, then we're getting more complex. First off, for n-grams, how does it work? Well, basically, n-gram will see there usually is like a start of sentence token here and an end of sentence token here. So these are all the tokens. So we would, split everything up into this, and then, so the n-gram would be given the start of sentence token, and it would say, So n-gram just means the n can be any number. It can be a unigram, which just means it's randomly selecting a word based on how often it appears in the corpus, based on just like basic probability. A bigram is it's selecting a word based on the one word before it. A trigram, it would be the two words before it, and so on. So basically, let's do a bigram model. So for a bigram model, it would look at this. It would look at the one word before it, so the start of sentence token, and then it would say, what are the most common words that appear right after the start of sentence token? Let's say, in this, okay, let's do one other sentence. A cat bit a dog. So in this corpus, the only two words that come after the start of the sentence token are the and a. So the next word has to be the or a. So actually, let's do one more sentence in the corpus. Huge cats bit tiny dogs. Wow, these are really violent. Anyway, so it can either be the, a, or huge. Actually, a cat bit some tiny dogs. So it can be the or a. Sorry, that's the final. It can be the or a. However, the only appears once, but a appears twice after the start of sentence token. So basically what this means is when the n-gram is doing its magic, the is going to have a 33% chance of appearing, and a is going to have a 66% chance of appearing. So if you run the n-gram 3 times, it's probable that you'll get the 1 time and a 2 times, because that's kind of the probability of the corpus. So let's say we do a. What comes after a? So if we're doing a bigram model, it's just what comes after a. If we're doing a trigram model, it would be what comes after a and the start of sentence token. However, it is different. So if we're doing a bigram model, it would have a 66% chance of being cat and a 33% chance of being dog. However, if we're doing a trigram model, looking at the 2 words before it, it would have an 100% chance of being cat. But let's say we're doing a bigram model. Let's say it picks dog one of these times. So then what comes after dog? Let's say we're still doing a bigram model. It's either period or 8. If we're doing a trigram model, it would have to be period because it would be based off of a dog. And, this is the dog. This is just a demonstration of how n-grams work. So now we're going to go and code it. So yeah, first we're going to do one for characters. So what this means is we have to read this list of lines. We have a list of lines right now, but what we want to get is a list of characters. So let's do that. Okay. Actually, let's start with words. Let's do this in reverse order. Word list. Or let's make all of our lists first, actually. Word list of words. I think I will want to exclude punctuation. And also I might want to get rid of stress. Actually, I'm not sure. We can do that later. So I will want to exclude punctuation. So our word list, we're going to instantiate list. This just means we're making a list. Punctuation. And we're just going to, put out, list all the possible punctuation that we have. We can always modify this later depending on how we want the program to work. But I'm just going to input all of the punctuation I remember putting in this corpus. And the reason I did the backslash quotation mark here is because if I just did the quotation mark, oh, actually that does seem to work because I did some weird, okay, well, hopefully that works. Yeah. Okay, awesome. So we're going to say for line and line list, which we've already made, for character and punctuation, line is the line replacing the character with the empty string. So it just means we're deleting all of these. We're going through each line, and then for each line, we're going through each character, each punctuation character, and we're getting rid of it. All instances of it in the line. And then we are going to, then we're going to put the line in lowercase just because I think maybe there are some instances in which I had uppercase letters, but I just, they don't matter to Delaney like they do for German, for example. So I think we can just make everything lowercase. Then we're going to say tokens is line split. So split, before we split based on this new line character, we can split based on anything, but if you leave this empty, it just splits based on spaces. So this is going to turn the string, the dog ate the cat, into a list of 5 elements, the dog at the cat. And then we are going to say for token in tokens. So for each of these, we're going to append it to the word list. So this looks very familiar to the code we have right there. And we're going to be using code that looks like this all the time. Token.lower. So this should create our word list. And we can test it by saying, let's pick a random word. Nuchka, another random word. Dala, another random word. Duomo. And so on. We're generating all of these random words from the corpus. Awesome. All right, so we have our word list. Now let's make our character list of characters. So basically, in Python, you have strings and lists. Lists are lists of items. Strings are just they could be any amount long of just text. However, what strings actually are lists of characters. So this is actually just a list, A, V, L, W, N, so on. I mean, it doesn't exactly work that way in Python, but that's how you can imagine it. It's a list of characters. And so what we could really do is we could just have one long string that's the whole corpus, and that would be our character list, probably excluding punctuation. So we already made our punct thing over here, so we don't have to do it again, but char list is a string, and we can say char list is actually our word list joined. So what this means is we're taking our word list of a bunch of random words like this. Oh, actually, wait, there were commas. Something has gone horribly wrong. I'm not sure if we want or don't want those commas. Let's say no commas for right now. Yeah. So it's a bunch of these words. Oh, there was just a comma. Oh, it's because we didn't run this again. All right. There should be no more commas. Oh, this is interesting. There is a stress vowel. I'm not sure if we want that to be in our final model, but I'll leave it for right now. So yeah, it'll be interesting to see if our models predict the stress right or not. Yeah, so back to character list. So our character list is the word list that we just made of these words, but joined by spaces. So this is the opposite of split. We are just making them into a string joined by spaces, and we can see that we can print the first few items of our character list. So character list, let's print the first 20 characters. Or yeah, oh, because we didn't run this. All right, daisa bangu tarasu. Yeah. Cool. So they do have spaces because we're joining it by spaces. So careless like includes the character space as one of its characters. That's useful to know. Awesome. So we can actually, I'm not sure if we should make these phoneme, syllable, and morpheme lists just yet. Let's just experiment on the character and word engrams and build our engram, stuff up. So we're going to define a function called engrams from text. So it's going to take, so this is just going to get all engrams from text. And what I mean by that is when we had our corpus of just, maybe I should have just kept this here, but the dog ate the cat, a cat bit a dog, so on. It's going to, by getting all engrams, so, and n is just like 2 if it's a bigram, 3 if it's a trigram, and so on. Let's say it's a bigram. So to get all bigrams, the computer's gonna go through this corpus. It's gonna say the dog, here are 2 words. It's gonna add, quote, the dog to a list. Then it's gonna add dog ate. Then it's gonna add ate the, and so on. So our engrams list is here. We're going to iterate through the list, grabbing engrams along the way. So the reason why we're doing minus and -1, it just means that it's basically because if we have the dog ate the cat, but we're like we only have the, if we're doing a trigram model and we only have the, we can't really generate anything because like we only have 1 and we really should have 2. Because for a trigram, it's based on groups of 3 words. So in order to generate 1, we need the 2 before it. Similarly, if we're at the end of a text, like if we're at the dog, so if we're here at dog, it's not going to be able to have a bigram starting with dog. And so that's just what this means. Engram equals list I to I plus n. Basically, also, if you have like any ideas about this series, like maybe I should just do all the coding before and then like show you guys how it works. But I thought it would be nice to live stream my progress because I don't know, I like watching stuff like that, so I think it's useful. But if you guys think I should just like write all the code before and go faster through it, I will totally do that. Feel free to also put me on like 2 times speed or something. Yeah. So now we're gonna make something called pre-engram count. So this is a dictionary. You don't really have to worry about it. I'll explain it, but dictionaries are basically like dictionaries. Dictionaries in Python are basically like dictionaries anywhere else. You have a key, which is, maybe the word in the dictionary. And then you have a value, which is the definition in a dictionary. So in this dictionary, in Python dictionary, the key can be anything and the value can be anything. It's just a way of searching through values that you want to be related. So the key is going to be our n-1 gram. So if we're doing a trigram model, it's going to be a bigram. If we're doing a bigram model, it's just going to be a word or a token, and so on. And the value is going to be the count of this n-1 gram, meaning how many times it appears in our corpus. And then the n-gram count is going to be the same thing, with the key at least. And then the value is going to be another dictionary where the key is the final character in the n-gram, and the value is the count of the n-gram as a whole. And we'll see why this makes sense later. So for each n-gram in our list of n-grams, the context, what we'll call the context gram, is a tuple. There's just, you don't really have to understand like exactly what the Python stuff is, but I'll try to explain it basically. But like the actual stuff like tuple, you can look this up. It doesn't matter as much to the spirit of the program. It's kind of just how we make it work with how Python treats different classes of numbers and lists and so on. The last character is n-1, just means is just going to give us the last character in the n-gram. And maybe instead of character, I should be saying like token. Yeah, last token, so that it works for any model. This is the tuple of first n-1 characters in the n-gram. And tuples are kind of like lists, so you can just think of it that way right now. So if the context gram is not in our dictionary, so this is just saying, is it in possible n-1 gram? I mean, no, because currently the dictionary is empty. So the answer is going to be no here. And not so basically what we just did is we're running through each context gram or each pre-n-gram, and we're saying, are you in this list of pre-n-grams? If the answer is no, we're going to add you. If the answer is yes, you're already in it, then we don't have to add you. That's what this is doing. And we're saying, so if you're not in it, we're going to add you, and we're going to make your value 0 because the value is the count. And if you're already in it, we're just going to increase your value by 1 because we're seeing you another time, and the count is how many times we're seeing you. And we're going to do the same thing for n-gram counts. And so here, since the n-gram count value is another dictionary, we're instantiating that dictionary here. This should be last token. My bad. So it's basically doing the exact same thing. Then we're going to make 2 more dictionaries, one called pre-n-gram frequency. Oh, I did not put frequency there, but frequency. And the second called n-gram frequency. And these are just going to be, I mean, we'll see, but they're just going to be the frequencies of the n-grams and pre-n-grams in the text. Pretty straightforward. So for each pre-n-gram in our dictionary of n-1 grams, pre-n-gram, n-1 gram, same thing. We're going to make a pre-n-gram frequency dictionary entry for this pre-n-gram. And the entry is going to be, so the key is going to be this, and the value is going to be what we're inputting here. The count of that pre-n-gram over the total number of n-grams. So this is just basic probability. Count over total counts. Count of what we're looking for over total count is the probability of what we're looking for. And then same thing for pre-n-gram and n-gram counts. N-gram frequency of the pre-n-gram is of course a dictionary, but then for last token in n-gram counts of our pre-n-gram forgive my IPA keyboard. So what this is doing is we're not saying, like, the n-gram frequency is not just the frequency of our n-gram over, or the count of our n-gram over the count of however many n-grams there are just total in that corpus. Actually, what we're saying is it's the count of our n-gram given our pre-n-gram. So it's not saying how many times does the dog ate appeared over how many times does every sequence of every 3 words appear in the corpus. Instead, we're saying how many times does the dog ate appeared given that the dog appeared. So that's that. And I think that's it for this. I think that's all we need to do. And basically we're just returning these frequency dictionaries that we've created and passing through n, which is, the n in n-gram. All right, so this should get all the n-grams from our text. Oh no, we have an error. Okay. I don't know why we have a, I'm not sure why that was there. Cool. Typo. Awesome. So now we should have all of the n-grams. We can look at what the output of this looks like. We can say n-grams. We're gonna run n-grams from text with the list. Let's say we're doing it with word list, and then bigram model. And I'm not sure, will it print out the output? All right, so this is what it looks like. So remember, it's returning the pre-n-gram frequency dictionary, the n-gram frequency dictionary, and then n. So this is going to be the pre-n-gram frequency dictionary. This is the, so this is just an example of the first few lines of the pre-n-gram dictionary. Since it's a bigram, our pre-n-gram is just one word, and these are the probabilities of them appearing in the corpus. Let's say it's a trigram, then it's 2 words, and if it's a 4-gram, it's 3 words, and it's just going through dai sabang, sabangu, bangu darasu, gu darasu dautru, and so on. And if we make it like 8, these probabilities are going to get way smaller, because right now they have like, actually they might not, because that's just basically saying it appears once in the corpus. But if we make it 2, hopefully some of these probabilities are going to get a bit bigger. Yeah, awesome. Awesome. So, cool. So that's what it's outputting. So now we're going to use this probabilistic list that we've created, probabilistic dictionary, to generate text. So we're going to define another function, define ngram gen, generate text with ngram. So our model, length, and setting is what we're going to be wanting. So I think like length is how long of a text we want it to generate. Model is our this. We're just going to be inputting this. And then setting is what lists we're going to want to do it on. So first we're going to say pre-ngrams, ngrams, n equals model. Then we're going to say, and so this is just basically copying this. Then we're going to say pre-ngram keys is the list of the keys of pre-ngrams, the dictionary pre-ngrams that we made up here. Or wait, where is that? Or the dictionary pre-ngrams is the dictionary pre-ngram frequency. The dictionary ngrams is the dictionary ngram frequency. We're just having them by easier names. So pre-ngrams keys is going to be the keys of this, which is going to be, if we look at where we make this, it's just going to be all the pre-ngrams. Then pre-ngram indices is going to be a list of numbers corresponding to the keys. Yeah, so it's just going to be like 1, 2, 3, so on, to n, where n is the count of unique n-1 grams. Because pre-ngram keys is like a list of the unique pre-ngram, pre-ngrams. List of all unique n-1 grams. So pre-ngram probabilities is a list of the values of the pre-ngrams dictionary, because the values were just the probabilities. List of all n-1 gram frequencies. Our start index is going to be, and this is just like whatever n-1 words that we're starting with, because like we said before, we can't really start with the in a trigram model, because how are we going to predict the next word? We need 2 words to predict each next word. So here we're just generating however many extra random words we need at the start. And this just means we're generating a random number in this list of numbers, weighted by the probabilities of all the pre-ngrams. And we're choosing n-1 of these. So yeah, this chooses random number within range of how many n-1 grams, or how many unique n-1 grams there are. Weighted by their probabilities. Cool. And then sampled is going to be a list of the start characters, n-1 however much we need. All right. So this just means, do this however many times we say in length. If n equals 1, so this is just for unigram models. The previous character is just nothing, because we don't need anything. n-1 grams don't exist, because 0 grams don't exist. They're just 0 words. So else, the previous is the tuple of sampled. So sampled is how we started our generated text up here. This is some weird code. I don't think you really need to, worry over this. It's just kind of aligning lists and, making sure numbers line up. But it's just saying that the preceding context is the n-1 gram or n-1 tokens from the sequence we sampled above, or we sampled so far. Yeah, I don't think you really need to worry over that. So then we're going to do possible next tokens. There's a list of n-grams. There's a list of the keys that correspond. So this is just saying, like, if we have already generated the dog, our possible next tokens are only tokens that have appeared after the dog, if we're doing a trigram. Not like giraffe, unless the dog giraffe exists in our corpus. So yeah. Then we'll do next token. Abilities is a list of the next token probabilities based on what we've just seen. Yeah. Then we'll say maybe next token probabilities normalized, or normalized probabilities is an array. So this just means normalized means they add up to 100. Basically, next token probabilities is our existing probabilities over their sum. It's just making sure that 1.0 means 100% chance. So this is saying we're going to randomly choose from all of the possible next tokens, weighted by their probabilities. Pretty simple. And then we're going to append this next token that we've just chosen to the end of our sample text, and it will, continue on with the previous context being including that token now. So yeah, let's say if setting is word, we're gonna, like, if we're trying to generate a word, if this is kind of if this is a phonological n-gram, then we're gonna join things with the empty string because we don't want spaces between our characters. But if the setting is text, meaning we want spaces between our characters, we're gonna join them with a space. So awesome. Let's see if this worked. So let's just run it. Awesome. No errors that we can tell right now. So down here, let's say, is this okay? We can delete this. Down here, let's say we are going to first we have to create our n-gram model. So n-grams from text. Let's do words first. Word list. Let's do a bigram. And then we'll say n-gram gen. So let's say let's define this as first n-gram model. So that will be our model. And then length setting, let's generate 10 words. And let's have them, so that we're generating words, so our setting will be text. Wow, so we just generated 10 words in the Lini that have never existed side by side. Waji no achikara kesaga 어제와 같이 왠지꾸라 밖으로 미스원님. So these words have never existed side by side before, hopefully. Yeah, so awesome. We have generated text with our n-grams. Let's put a check mark here. We're gonna fine tune this. Like, there's definitely some problems, but we're gonna basically spend the rest of this episode now just fine tuning this model, figuring out problems. These problems might be specific to your corpus and your Conlang as well, but yeah. And then we're gonna build some tools to transfer our corpuses into lists of phonemes and syllables, and that's actually gonna be pretty hard, unfortunately. Yeah. But it's cool that we've, now generated new text in our Conlangs. So if we make the model a trigram model, it will generate it based on so it's saying we picked Ligoa randomly based on weighted probabilities of how often it occurs in the corpus. We picked Migachin from all of the possible tokens that appear after Ligoa in the text based on weighted probabilities. And we picked I based on these two. Since it's a very small corpus, remember sparsity is the biggest issue. It's probably likely that Ligoa Migachi appears once in the corpus, and therefore I is the only possible thing that could have appeared after it. However, I don't think this full line appears in the corpus in any one place. Like this part might, but I think here it kind of, this definitely does, but I think here it kind of gets mixed up. So it might be taking from a few different of my translations. However, if we increase this to 5, this I can even remember what comes after it because it's all from Gashi. It's all from one part of our corpus. And this is because sparsity. So yeah, that's the biggest problem with n-grams when you have a really small model. However, right now, let's just use our bigram model, or maybe even our trigram. But Pokemonji sabashukanda kanda ajike kami wadang nitani nakagawa. Okay, so that's our random words. These are all words that I've put in one of these translations. But now, let's do character list. We're generating words, and let's say it's we're generating words with a length of 20. So they won't actually have 20 characters in a row. Instead, it'll be, because we included spaces as characters in our character list. So like this. So yeah, there should be spaces. Yeah, so there are spaces. Oh, this is a bit ugly. Starts off with a space. So dire is supposed to be one word. Oh, so we have a dash there. I did use dashes a few times in a corpus. And then there's a word with 2 different primary stresses, which does not exist in the Lini. So wait, let's make a list of issues to fix. Issues to fix. Dashed words. Stress. Yeah, let's try again. Oi. So that's terrible. I think it's technically phonotactically sound in the Lini other than 2 A's next to each other. I'm not sure where 2 A's next to each other could ever have appeared in the corpus. Let's see. We can actually test this. So for word in word list, if is in word, I think this should work. Print word. Let's see if that works. Oh, it's wa, the exclamation used in my Pokemon translation video. So that's where it's getting that from. Interesting. Okay. Well, cool. Let's generate some more random words. Oh my god, that is so ugly. So the reason it has a double M is probably just because it got cut off. Like, hopefully, if I had put 21, the next character would have been a vowel. But this, like, first of all, there's 3 A's in a row. Second of all, there's like 4 different primary stress. Oh, this is so gross. This does not look like Delaney text at all. Okay, let's move up the let's make it a trigram model. Okay, so that's maybe a little bit better. Yeah, okay, this is better. This is doing better. Like chigoge kishaga la. So this is cool because none of these, I mean, apart from la and maybe ge, I don't know, are actual. None of these are actual Delaney words. However, they look like Delaney words. Okay, this is pretty bad. I don't know why there are so many long words. I guess it's just because like a space is so improbable. This one's better. Dibanju totally could be a Delaney word. Siwonichema, I don't know, maybe. Simujiboma Naijinyoko. Like, maybe the dash is definitely a problem though. Satuma Kiswotumire. Well, Suwotu comes from Spotify, which was my translation of Spotify. I don't know where, but yeah. But otherwise, this is pretty good. You know, if we increase it more to like 8, maybe it will just copy words, presumably. Oh wow, it's taken a while. Okay, presumably there is something before that. Yeah, I think this is just copy. Let's try again. Some avatal probably. Ajike kambi wada chime. So yeah, so these are all Delaney words, I think, but they're not, you know, I don't think these have ever occurred together because like, so if we're doing based on the 8 characters before it, it'll be 1, 2, 3, 4, 5, 6, 7, 8. So anything without before it, you know, that's what we're basing off of, which is still a lot. So yeah, but anyway, we've created character and word models for our Conlang. So now let's do phonemes, syllables, and morphemes. Okay. Whew. So let's just check. Actually, let's fix our issues first. So dashes and stress. So how can we fix these? Well, dashes, we can just go up here and say, oop, there's a dash. That's part of our punctuation. Should be good now. And then for stress, we can also here, we can make a list of vowels. Or a list of unstressed vowels, sorry. O, U, or I mean, these could be stressed. Stress is not always written in Delaney. In fact, it's most often not. It's only written when the stress rules are actually like violated. So the stress vowels are oops, and ooh. So we'll say I think we'll say like for I in, or wait, let's do this after we do the lower thing. For I in range of the length of the stressed list, we're replacing all stressed things with the unstressed things, or the non-marked stressed things of the same index. So we're replacing this with this, this with this, and so on. So hopefully now we shouldn't get any more, let's do like 4. We shouldn't get any more stressed vowels. Oh, that's so fun. Okay, well, I think we just have to run all of our programs again. Like, well, actually, these don't need to change, but now hopefully we shouldn't get any. If we do this a ton of times, we're not finding any stressed vowels. Awesome. And these actually look pretty good. Isakurogne kankyoshi. Something here. Donne bang. Okay, well, this couldn't work. Huh. That's interesting. Because the leading words can't end with ng. Only with n. But maybe somewhere in the corpus I ended something with ng by accident. Opakura. Hinyo kimanurua dirashua. Like, it's phonotypically sound in the Lini, but like it's really long. Why are they so long? Anyway, yeah, so let's make let's check these off now. And you know, throughout the series we'll work on fine-tuning these later. It's just important right now that we have them. All right, phonemes, syllables, morphemes. So we already have our morpheme marked corpus. So let's just do that one first. Let's read in morph line list of morpheme marked lines. So it's going to be the exact same thing, except morph line list. And instead of unmarked, it's going to be marked. Our folder marked here. So we're going to be reading in these things with all the dashes. Oh, so maybe we're going to have to change our dashes a role, but yeah. Awesome. Oh, no, something hasn't been found. Oh. Oh, because these are called, these have different names. They have marked after them. Oops. This is like this, I guess. All right, so now it should work. Awesome. We can also go down here and just like, oh, let's do that later. So word list is going to be from line list, but we can make an alternate word list, or we don't want a word list, but a morpheme list. Morph list of morphemes with, I think we should do with spaces between words counting as morphemes, kind of like, because we're gonna end up putting the morphemes together and we want to know when there are spaces. It's kind of like the character thing. So morph list for line and morph line list. The line is there is punctuation here, I assume. Yeah, there are periods. There are exclamation marks. Cool. So we'll just steal this. Then we'll say for in, let's steal the stress thing. And then let's do something about the dashes, because actually we don't want, so let's remove the dash from here. We can make a separate rule here. We can say line equals line replace dash with space. And then over here we won't be replacing dashes. Instead we can have a new rule for dashes, and we can say like, so I think we say line equals line replace, we're going to replace dashes with a space and then a dash. So this is going to turn a word like samyoshikamu into samyo. So this is good because it will tell us that chika and mu are suffixes, but samyo is not. Samyo is like a root. So yeah. All right, so now we'll make our list of morphemes by splitting it. Same thing we did with, I mean, we could also just call this token, but yeah. Yeah, it might just be easier to copy this, and then we'll append this to morph list. Awesome. Do we need token lower? Wait, we already did. Huh, why did I do this twice? Token. Awesome. So hopefully now we should have our morph list. We can go down here and check. Print morph list. Let's do 220. First 20 morphemes. Daisa banggu. Yeah, they're all single words. Dalasu. What? No, these consist of multiple morphemes. Why isn't that working? Morph list. So, okay, let's go back here. Morph list. For line and morph line list, for character, we're replacing punctuation. There shouldn't be anything wrong with that. Unless dash is still here, but it's not. Oh, maybe we need to run this again. Let's try this again. Okay, so that was the problem. Now we have dala, su, dauta, ru, noa, ru, towo, ra, so on. Awesome. All right, so we have our list of morphemes. So now we can basically just make another model. So our morpheme model is n-grams from text, and then morph list. Let's say it's a trigram, and then n-gram gen. Morpheme model. Let's generate 20 morphemes.
Okay, so I encountered a bug, but I'm back. It took me like 2 hours to resolve it, but we're good now. We fixed it. And now I'm just making nice outputs for each of the models we've made so far.
Okay, word model. Okay, this is completely parroted. By parroted, I mean like a parrot, copies your words. So parroted, this is just totally copied from one of my things here. Yeah. Oh well. Daihoto churawirejo. These could totally be Dolini words. And then morpheme model. So maybe we make it text, cause yeah. Don't think it's putting spaces there. Okay, so here we go. So it's putting spaces between everything, but we want it to combine the morphemes into the words. So maybe we now print, we now make something called combined morphs or let's say morpheme output equals this. So first we're just gonna print that, and then below it we're gonna print, so for morpheme, oh, but it's returning a string, so we can morpheme combine morphs is morpheme output, but replacing space dash with empty string, and then we can print combined morphs. Let's try that. Okay, awesome, that worked. Numero no oro ujega hache sava ki sahwa wa numero no oro. This is definitely also copied, so let's make this, or let's just generate it again to see. Lala chisi namashkala ki sahga ujewa hachi ku dagiro no chikawai jigo. Lala chisi namashkala ki sahga ujewa hachi ku dagiro no chika Okay, I don't think that's totally parroted. This is definitely not. Uiko 군도님이 지사나라이라 주라기가시 또는 제반돈치다. Okay, that's totally parroted. Maybe we make this a bigram. We can actually even up this. See what it does. Pisato jidda samoji something. And this is actually fine because presumably it got cut off and can occur together at the start of the word in Dolini. Shimondo tikundo pisatomaso chuiraurani raningira in chida waso. Like, I think it's not totally parroted, but a lot of parts of it are. And from here, yeah. So even with just a bigram, a lot of this is parroted just because of sparsity. But yeah, so we made our morpheme model. Let's check it off. Now we just have phonemes and syllables. And the problem with phonemes and syllables is that we need to now write programs to get from romanization to phonemes in Dolini. And we also need to write a program to get from that the like phonemic encoding to syllables, and that's pretty hard, but we're gonna do it. So we're gonna do it right now.
So you know how I just said we're gonna do it right now? Well, actually we're not. We're gonna do it next time because I split this episode up into 2 parts because romanization and syllabification took a pretty long time. So we're gonna do that next time. It's gonna be great. Yeah, so thank you guys all for watching this one. And yeah, if you have any ideas about how I should structure these episodes, longer, shorter, please put me on 2 times speed. You know, more structured, less structured. Please let me know in the comments, and I hope you guys are still here following along. And I think we're gonna make some really cool models together. So yeah, see you next time.